DNA replication. What is DNA made of?
Well, it's made of the those four things.
It's made of four things. Is that what you said?
It's made of uh, A, T, G, and C.
Okay, so it's made up of A. That's not
Adenine,
it. Added. Okay,
thymine,
so it's made up of adenine,
thymine, thymine,
thymine.
thymine, thymine,
I don't know if it's thymine
guanine,
or thiamine, but I'll spell thymine. That could be wrong. Thymine, cytosine,
and guanine.
and guanine. And what are those guys?
They're purines and pyrimidines.
That's a good answer, but more specifically, they're nitrogenous bases.
Hmm.
Sometimes they're just referred to as the bases. So they're
And
not
in RNA, thymine is replaced with uracil.
exactly. Okay, so there's two types of nitrogenous bases, and you could think of one as being a snowball, and you could think of the other one as being a snowman. I'll draw the snowman like that. Okay, and so you see how one of them has one ring,
Mm-hmm.
and the other one has two rings. Okay, so if you think of a pyramid, that's the worst pyramid ever. Okay, so if you think of a pyramid, how many rings make up the base of a pyramid?
Just one.
Just one ring. And did you know that I have a friend and his name is TC? TC. I don't know what it stands for, but that's his name. Maybe it's, I don't know, actually. I was going to say something funny, it would have been just lame. Okay, so TC. And TC lives inside of a pyramid. He lives in a pyramid. So that's how I remember that thymine and cytosine are pyrimidines.
Okay.
Okay, so the pyramid involves a single ring, and that involves thymine and cytosine, which tells me that adenine and guanine are the purines, and they're both nitrogenous bases.
But wait. Uh.
Yeah.
So the ones with two bases, with two rings.
Oh wait, I
What?
just said that wrong. No, I explained it
I
right with the
was.
pyramid, and then I just did it backwards. So, oops. So no, this is TC. What am I doing? This is the hexagonal pyramid right here. TC lives in the pyramid. So this is pyrimidine.
Mm-hmm. Actually, that acronym works well because we call our fencing coach TC.
Oh, and you could think of him as being a real square. Okay.
Yeah, he is.
Okay.
So I'll remember that acronym.
Hold on one sec. Oh, it's texting me. Okay. So let's see. What else? Okay. So here, if you think of DNA as a ladder,
Mm-hmm.
do you know what the rungs of a ladder? What rungs are? What that means?
No,
No?
I do not
Wrong.
know. I do not know what a rung is.
You should, but I gotta be honest with you, I didn't. I was your age. Rungs are the part that you step on.
I mean, I don't know it by name.
Huh?
I mean, I don't know them by name.
But you definitely know that you step on ladders.
Yeah,
Okay.
I've used a ladder before.
You got that one down. Wait.
Yeah.
So actually, rungs. So this is, oh no, actually, I was right. This is DNA. This whole thing. DNA, there you go. and these are the rungs of a ladder,
Right.
and these are the sides. But you can consider the rungs, and think of the rungs actually as being made out of rope. So, kind of the ones that throw off of helicopters to save people.
Right. Or like the obstacle course ladders.
Right. So you have that. The sides you're going to want to think of as being the backbone of DNA of the ladder. Okay, that's where it gets its structure. So this can still be made out of like metal, but this is rope right here. Okay, so this part is really strong. Okay, now the rungs, let's go down over here. Oh, actually, I'll just draw right on top of this thing. So the rungs are your nitrogenous bases. All right, so you're gonna have a pyrimidine right here.
Bonded to a purine.
Huh?
Bonded to a purine.
Yes, exactly. So you're gonna have a pyrimidine bonded to a purine, so a snowman with a snowball, and you're never gonna have two of the same bonded to each other.
Right, because together you get the 3 balls of the snowman.
Exactly, and if you had 1 and 1 or 2 and 2, then DNA would not look like a ladder, and DNA would be like, whoa, like that.
Mm.
Does that make sense?
Yeah, and I know that T bonds with A and C bonds with G.
Yes, that is correct. And so, yeah, so your pyrimidine, well, what is this, a purine or a pyrimidine right here?
That is a pyrimidine.
This is a pyrimidine, and who lives in a pyrimidine?
TC.
So here's your T, and here's your C. What is this right here?
That's a purine.
Purines, this could be, maybe let's say this is like, well,
G.
actually, if this is C, this has to be G, right? And I can't remember C goes to G anyway, because I can turn a C into a G. Okay, and so...
Now I'm thinking TC is like Tom Cruise living in a pyramid.
Okay. So you have these purines and pyrimidines, which are like the rungs of a ladder, which remember are made out of rope, and they're bonded to each other. These are the ones that are across from each other. Do you know how they're bonded to each other?
I do not.
They're bonded by hydrogen bonds, and every textbook in the world draws hydrogen bonds by red dots.
Okay.
Like that. Those are hydrogen bonds. And hydrogen bonds are weak.
Right.
Weak hydrogen bonds.
But
which is why
that's necessary, right? So they can be broken apart when the replication happens?
Exactly. And that is why I want you to think of it being as a rope ladder versus the strong beams on the side right here. Now this part over here, the side is what they call the backbone. And the backbone is made up of, I think, 3 things. You have a sugar, actually a 5-carbon sugar. Do you know what else is on the backbone?
There's a phosphate group, right?
Yes. So you have a 5-carbon sugar. You have, so your backbone is made up of a 5-carbon sugar, a phosphate.
And what is is a hydroxyl or carboxyl is the last one?
Wait. No, that's it actually. It's just the phosphate and the 5-carbon sugar. Because they always call it a sugar phosphate backbone.
Okay.
It's called a sugar phosphate backbone. So you're going to get your 5-carbon sugar, which in this case, by the way, your 5-carbon sugar is called deoxyribose.
Right.
And in the case of RNA, it's just called ribose. Ribose. Okay, so when you draw that 5-carbon sugar, you can draw it as a pentagon. And then you have a phosphate, like that. And then over here, you're going to have another, like, here, I'll show you sugar phosphate backbone. show you a better picture. Oh, that's good. I don't know if you can see that. No, that's not good. Hold on. Yeah, that's cool. So, if you see right here, the green guy, the yellow guys are the phosphates. You see it?
Mm-hmm.
Okay. And our little pentagon here, and you can think of the pentagon as being your 5-carbon sugar, because the pentagon has 5 sides. You with me?
You.
But that's not exactly how it works as far as the 5-carbon sugar, because if you look over here, man, if you look at a DNA molecule, I don't know if you can see this, but in this pentagon, the top part of it is an O.
Yeah.
Okay, well, that they just said it was a 5-carbon sugar, but that would make it a 4-carbon sugar if one of those things were taken up by an O. So if you go like that, one sec. That, you have an O right here. And that's because the other carbon is right here. There's carbon 1, and actually carbon 5, one second.
No, that's carbon 5.
That's carbon 5, yeah. That's carbon 5. And then your 1 is not that one.
No, 1 is it?
Wait, where? Hold on one second.
Okay,
I'm just kind of making it up. Wait, hold on. But the point is...
No, because I can...
Huh?
Okay, I keep wanting to point at it. It's like, that's going to help.
Here, let me draw... I'm going to draw the way it is in this textbook. It's like... Where the hell is it? Oh, wait, hold on. I'm not actually looking at a picture of it. Do you know how it looks?
Yeah.
Oh, here we go. So it goes like this. Like that, like that.
That's the first one.
Like that, like that, like that. And you're saying this one's the first one?
Yeah.
That makes sense. And this one over here, bloop, bloop, would
That's
be
the 5th one.
number 5.
Right.
Let me make sure that's right.
Because then you'd have 2, 3, 4. Yep.
And yeah, that's right. So then you have 2, 3. So the 5th one is actually not part of the pentagon. Right? And then over here, you have your phosphate thing. Okay.
You circled a 5, that's giving me OCD.
What's that? What'd you say?
I'm getting OCD because that the 5 is the only one that's not circled.
Oh. Here, let me just fix that for you.
Oh, okay, nice.
Okay. Alright. One other, well, lots of other things. Hold on one second. So, you have, let's just go. Okay. So, DNA, you could think of it, DNA looks like, the way one strand is with respect to another is like shoes inside of a shoebox. Right? You have one shoe like that. That's a shoe right there. And then you have the other shoe like that, fitting inside the shoebox. So you have
skinny calves.
Yeah. 5 prime. That would be like a 5 prime end, and then it would correspond to the 3 prime end. But then this side over here would have to be the 3 prime end.
Right.
And it would correspond to the 5 prime end. Does that make sense? And so they say that DNA is anti-parallel.
Right.
Okay. Now, if you think of skateboarder on a skateboard ramp. Ramp goes like this.
Mm-hmm.
And let's say this ramp, let me see, is 5 feet up.
Okay.
5 feet up. Alright. And the skateboarder is right here. And the
Nice.
skateboarder's, that's the skateboard. And the skateboarder is going this way.
Mm-hmm.
Okay, skateboard's going that way. You notice how the skateboarder is riding on top of the ramp? Wait, before I become awesome, let me just make sure I'm right on this one. Hold on. Wait a minute. I'm so proud of this. Hold on.
Wait, did you turn off video?
Oh, no, I can't see you anymore. Hold on. Okay. You ready?
Mm-hmm.
Okay, so, the skateboarder, so is the guy that's moving. So the guy,
I can't see your screen.
oh man. Okay, so the guy that is moving,
I like the guy.
the guy that is moving is starting at 5 feet
Uh-huh.
up. Okay? So when you think of DNA replication, you have something that's staying still.
Mm-hmm.
I don't want to draw it down there. You have something that's staying still, and you have something that's growing.
Okay.
Okay? So here would be the 3' end. Yep. And here is going to be the 5' end. And it's going to grow this way. Right? And I don't want to do it like that, but it's going to grow in this direction. So that means that this is the template. And this is the growing strand. And do you notice that DNA can only grow in the 5 to 3 direction? Just like the skateboarder is going to go down, is going to move from 5 to, you could say he stops at 3 feet if you want, whatever. But that's how I remember, because I used to confuse these. So it grows, but look, the skateboarder is growing at the 5 to 3, but reading off the 3 to 5. So it's moving from 5 to 3, but reading 3 to 5. Because the question could be, you have to be very careful when you read the question. You have to know whether they're talking about the template or the growing strand.
Mm-hmm.
You with me?
So wait, sorry, I zoned out for just a sec. Can you repeat that last part?
So you have to know when they word the question on the test, if DNA grows from 5 to 3 or 3 to 5. Does it grow from 3 to 5 or 5 to 3?
3 to 5, right?
Well, growing. So you're the skateboarder. The skateboarder is moving from
5 to
3.
3.
Okay? So it's moving from 5 to 3. Yeah, I could put little wheels right here too. So 5 to 3. And but it's reading 3 to 5.
Right.
Right? You have your 5' here and your 3' here. So the template needs to be 3 to 5, but it's growing 5 to 3.
Mm-hmm.
Does that make sense?
Yeah.
Okay. Now, the thing that actually lays down the nucleotides is called DNA polymerase.
Uh-huh.
All right, but DNA polymerase is a little stupid. So what's going to happen, I'm going to draw a strand like this, and I'm going to draw a strand like this. Oh, well actually we have to back up. Okay, so DNA has to get unzipped. You with me?
Mm-hmm.
All right. So if you think of
What is the helicase does that, right?
what's that?
Is that the helicase that does that?
Yeah, man, I wasn't telling my cute little thing and SpiderMan. Jeez.
Okay, well, I want to hear the Spider-Man
Well, okay,
analogy.
so I don't. You're too young to know this, but back in the day when Spider-Man came out, like the trailer for Spider-Man was like May. It was like I think Spider-Man was coming out like let's
The
see.
original, the live-action movie?
Yeah, the one with Tobey Maguire.
Yeah, of course I've seen that movie.
Okay, well that one. Well, you've seen that, but you haven't seen what I'm about to tell you. So the Tobey Maguire movie came out. I think probably came out in 2002. I would think, because
Mm-hmm.
Spider-Man's always come out in May for some reason, and so
All superhero movies do.
and so it probably came out in 2002. But in early 2001, there was a scene, Spider-Man Twin Towers trailer, and
Oh.
they deleted this scene. This is I would always forget what the different little proteins and enzymes did. So if you think of Spider-Man's web between the Twin Towers,
Mm-hmm.
and then you think of a helicopter coming along, you probably didn't know this, but I don't like to brag or anything, but I'm the best helicopter drawer out there. And you think of a helicopter coming along, that's how I draw it for my kids. Okay, a helicopter comes along,
With the happy
and
face.
the helicopter comes along, and it goes kind of like vertical. Its propeller is going to cut the web
Mm-hmm.
and ruin Spider-Man's web right there. So, and I think of a helicopter because that reminds me of Helicase. See? So Helicase breaks... Oh, I should have drawn these as red dots because what are biology books notorious for?
Hydrogen bonds.
They draw their hydrogen bonds as red dots. And so Helicase breaks the hydrogen bonds
Mm-hmm.
between the strands. It breaks the hydrogen bonds.
Between the donor strands.
Yeah. And so it basically, Helicase unzips DNA.
Mm-hmm.
Hydrogen bonds. Unzips DNA. Alright, you ready?
Yeah.
Okay, so the one thing about this process, I think, than what was on the last test with all that NADPH and all that stuff is, I think it's less abstract.
Mm-hmm.
It's more tangible. You can kind of picture this. So it breaks the bonds. But DNA, I mean, these are still things that want to come back together again. They're kind of like magnets, right?
Uh-huh.
Something needs to permanently keep it apart. We need to get some toothpicks, actually. Or dude, where's my awesome drawing? I got rid of it. So if you have DNA that's like this, and it's been separated, you got to stick some 2x4s actually right in here to keep this from coming back together again. Otherwise, it's gonna just re-zip again, right? So these 2x4s are called single-stranded binding proteins. And their job is to keep DNA, so these are the 2x4s. Their job is to keep the DNA from coming back together again, the opposite strands. You with me?
Yeah.
Okay, so here would be, well, I don't know. I kind of want to make DNA go this way, right? That's kind of my plan. So can you tell me what prime goes where? I want DNA to grow this way.
Okay.
So what prime is where?
That would be 5 prime.
5 prime, because that's how the skateboarder moves. 5 prime, I want it to go this way. That means this is 3 prime. That automatically means this guy is 5 prime,
Right.
right? And I guess if maybe I make this a different color. 5 prime.
And that would be the leading strand, right?
Yes, leading strand, there's no problems. Stealing my thunder. Leading strand.
See, I know some things.
You do know some things. You know, like, leading strand, and I was so excited to tell you about that. Okay, so leading strand, okay, so DNA, remember I said, so there's a molecule, actually an enzyme, because anything that ends in ACE is an enzyme. So you have an enzyme, we'll make it green, and it's called DNA polymerase.
Okay.
Alright, so DNA polymerase, it reads the template and lays down the correct nucleotide based on base pairing rules,
Mm-hmm.
which this guy named Shargoff came up with. Pairing rules. By the way, we didn't talk about something up here. What the heck's a nucleotide? A nucleotide is all of this. Right? It's all of this is a nucleotide. Just this piece right here.
Mm-hmm.
So a nucleotide consists of what?
A backbone and a nitrogenous base.
So you're gonna get your sugar phosphate backbone. Actually, let's just say it. Actually, a nucleotide is made up of deoxyribose,
Mm-hmm.
a phosphate, and a nitrogenous base. So all nucleotides are exactly the same, except for the fact that they have different nitrogenous bases. So when DNA polymerase comes along, it's laying down nucleotides. It's not laying down bases. It's putting backbones and bases in there. It's creating a completely new strand. So it's going to put a rail plus a rope, part of the ladder. Well, half the rope, right? It's going to put this part right here and plus this right here.
Mm-hmm.
Okay, and it's going to grow in the 5-3, but everyone's watching, everyone's excited, all the little molecules are getting together. This is like a miracle, and they want to see this. So DNA polymerase comes over here, and it's ready to go. All the molecules are super excited, and nothing happens.
Right.
Because the DNA polymerase can't get started. It's like those Formula 1 cars that have no first gear and you gotta push them. You know, I don't know if they still do that, but you gotta like push them, and then they're like, once they're in second gear, they can go.
Mm.
So you actually have to have its little friend that it needs, RNA polymerase. RNA polymerase doesn't go like this. And let's just say we have, I don't know, we have an ATCG right here, and then you're gonna have this guy coming along. Now it needs to have a different color, which is RNA polymerase. Because RNA polymerase makes what's called the primer. So RNA polymerase. Because DNA polymerase can only grow off of an existing strand. It can't start. It has no way of starting. So RNA polymerase goes like this, and it's like, all right, well, let's see G. G corresponds with C. Awesome. Remember, that's not just a nitrogenous base. That's the whole dealio. You're getting a base, and you're getting a sugar, and you're getting a phosphate. But I'm just writing it down as C because that's really the only thing that's different. Does that make sense?
Mm.
All right. So then RNA polymerase puts what right here?
A G.
G. Puts right here.
An A.
Aha! No,
A-
RNA
a U?
polymerase. A U. I was waiting for that. And then over here in A, it puts down a what?
No, it would put
Wait,
down an
that's
A.
not right. Oh man. Okay, this is an A, and then over here is what?
A U.
A U.
Yeah,
Okay,
it was right.
Okay, so I'm just like I was like a lion in the bushes. All right, so so it's doing everything just like DNA polymerase would, except when there's a T, it has to. I'm sorry, when there's an A, it's gonna lay down a U instead of laying down a T because it's RNA polymerase. So this thing right here is called this little strand. In my book, it's red, and it's called a primer. Which kind of makes sense. I like that name because primers you put on before you paint. Primer. Now DNA polymerase is like, alright, cool. Thank you for pushing me. So now DNA polymerase comes along. Did you lose me?
No. My
You can
video
see me
just turned
still?
off. Yeah.
Alright, cool. And so DNA polymerase comes along, and this is, I'll take it from here, RNA polymerase. So this is DNA polymerase. And then, if we keep on going, you have, I don't know, T, T, A, C, G. DNA polymerase comes along and lays down the corresponding DNA type things. So it's going to put the A here and the A here, and then the T and the G and the C. Okay? Now, one second. You have, okay, then you get another DNA polymerase molecule, another one, so DNA polymerase, and it comes along, and it's going to go, no, 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 that needs to be a T. Does that make sense? Okay. Then we have another problem. We have some nice hydrogen bonds going on right here. Looking pretty cool. Looking really cool. But what we don't have, let me make sure it's in this book before I say it. Oh, no, no, no. Everything is good. Wait, hold on. No, everything's perfect actually. That's it. So that's how you take care of the leading strand. Okay, this other strand, do you know what it's called?
Lagging strand.
The lagging strand. And how does a lagging strand work?
It's discontinuous.
Yeah, so it's not only discontinuous, it's kind of moving in the wrong direction. Kind of. It's overall, like, its net movement is correct, but the way it works...
it's like, it's kind of moving, like, uphill, right?
No, it's like, let's say my goal is to walk across the street. I'm gonna run backwards, then I'm gonna jump forward, and then run a little bit backwards, jump further forward, and then run backwards, then jump further forward. So, it's like, my goal is to go from here to here, and I'm like, alright, wee, wee, like that. And so, I mean, at the end of the day, I will have made it this way, but not the most efficient way to do it.
Right.
But except it's not one thing. It's not like one strand doing that. So what's happening is over here, since it can't read 3 to 5. It can only. I'm sorry, it can't read 5 to 3. It can only read 3 to 5. It's gonna go, and it's gonna find a 3 somewhere, like there, and it's going to go this way, and then it's gonna find another 3 over here, or like, you know, like that, and kind of like go, and then go that way, like that. So so you're just getting little fragments But at the end, you'll have your DNA. You with me?
Mm-hmm.
But what are those fragments called? The Japanese guy that came up with it.
The Okazaki
Uh-huh.
fragment.
Yes, Ogasaki fragments is what he called these little pieces. Man, discoveries are so easy back in the day. I totally would have seen that. So much harder now to discover things. Ogasaki fragments.
Everything's been discovered.
Everything's been discovered. So, is it Ogasaki? I'll have to spell it.
Okazaki.
Or
I
is it
think it's
okay? It's okay, right? Oh yeah, here it is.
yeah.
Okay. Okazaki. But now it looks like I wrote okay. Okay, Azaki. Okay. A little better. Fragments.
Right. And what are those? They're like the.
These are these little pink guys right here. They're the discontinuous strips.
Okay. So they make up the lagging strand.
They what? They make up, yeah, all together, they'll make the lagging strand. But we have a problem. The problem is that this strand, it's like, you know, when we did the backbone, we go like that, oh, there's DNA and there's DNA, and this one looks good, but this one on this side is like this. How good of a backbone do we have? We got a little backbone problem. What's our little backbone problem? Do you see our backbone problem?
No. Well, there's holes in it.
There's holes in it because the strand went like that, and then there's a hole, and there's another hole, and there's another hole. So we need to seal this up. We need covalent bonds.
Right.
To put these adjacent Ogasaki fragments together, and that's when ligase comes to the rescue. That's like the glue that glues these adjacent bonds together. So ligase. So ligase comes along and seals that up and seals that up. So something that I left out of this is, remember, the DNA polymerase cannot start on its own. It needs a primer. So that means you gotta prime this guy first and do that whole thing. And then DNA polymerase comes along and lays a strand, and another DNA comes along and swaps out all the U's for T's. And you got another primer here. And another primer here. Does that make sense? Yeah? Okay, and then, now you would think that this would take like a really long time. So, but that's not really, it doesn't really take a really long time. Because what's happening is you have a bunch of this happening at the same time on the same strand, like on different parts of the strand. So you'll have it happening here, and here, and here, and here. And then, so it's going to happen here, and this thing is called replication bubble. So when you're going to get your replication going on, and it's going to be like like that, like you're getting your replication. Does that make sense?
Yeah.
It does, because it's a horrible drawing. Yeah. So
Sort of.
that's a bubble. So if we zoom in our bubble, so I have a zoom in drawing right here. It looks like this, and you have they call this the origin of replication. And if you think about it, the origin of replication would kind of be, where did it go? I mean, it'd be here, it's where it starts.
Right.
You see, I just didn't draw the other, are you watching? I didn't draw the other piece of the bubble over here. There's a whole bubble going on over here. You're only seeing one side of it. So, that's origin of replication, and you have, they drew little red things to kind of show you that Oh yeah, it's that you have a primer. And then you can go. Like that. And then this is the leading strand. And then over here, you have the lagging strand because it looks like this. And then, oh, this makes a lot of sense actually. Watch this. And this goes like this. So why? Look how the red is right here.
Those are the primers.
Those are the primers. And then here you have, look, then you get one primer, it does this whole thing. Then over here,
Well, right, because the leading strand's continuous, it doesn't need more than one.
yeah, so here, this right here is a lagging strand. And this right here is now the leading strand. This right here is the lagging strand. But the picture that you saw earlier from me was just this
Right.
picture that was of the drawing that I did right here. It's just that part of the bubble. It's just this section. Does that make sense? Okay. So this is called the replication bubble. And the replication bubble is happening all along. These are all bubbles. Does that make sense? Bubble, 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 all along the DNA at the same time. So it's actually like crazy efficient and crazy fast, because you have DNA polymerases attaching to this all along the strand and making their own bubbles right there. And I guess you have those single-stranded binding proteins keeping it up. And I think that is it. Okay, a couple more things. So DNA polymerase is not perfect. So sometimes it lays down the wrong nucleotide. So it has to like repair. So you have DNA polymerase can like go out, like, so let's say you have, it actually does two things. DNA polymerase proofreads and repairs. So let's say you have, I don't know, C-A-T-C-A-T-T-C, and then over here you have, hold on a second, hi. Say hi to my son Christopher. This is Trevor.
Hey, Christopher.
He can't hear you though, because it's on my ear. What's up? You want to hang out right there? Only with me. I'll have to be downstairs though. Okay? I'll go. Alright, so I'll be there in a little bit.
What time?
It's like 10 minutes. Okay, he wants to look up troll faces on YouTube. But just so you know, my twins the other day looked up, they wanted to find something, but they can't really spell or read or anything. And just so you know that when you type in a bunch of C's on YouTube, well, you might as well be touching in a bunch of X's, because you get some XXX stuff going on YouTube. So if we have a smart TV and they punched in C, and oh my god, the stuff that was on my screen. Do you understand what I'm saying?
Sort of.
So the twins basically punched in C, on the remote on the smart TV that shows YouTube, right? And
Yeah.
porn popped up. Like,
Oh, that's kind of what I thought you were.
yeah. So that's why I'm like, YouTube's off limits. All right. I have to actually set up the parental thing on that, so it's actually off limits until I can figure that out. Okay, so
I didn't know that if you type in XXX it does that, but
I don't know. I would assume,
uh,
but I do know that CCC has the same effect.
huh.
Okay. So, CCC. So
We're done at what, in like 10 minutes you said?
yeah, really soon.
Okay.
But we're almost done with this. We're actually we're at a good stopping point. Okay, so do you see? So here's the original strand, right? So we'll say this is 5 prime.
Okay.
No, it wouldn't be 5 prime. Let's say 3 prime. And let's say
Right, so the
5.
template goes from 3 to 5.
Exactly. Now this, let's say we have DNA polymerase coming along, right? And DNA polymerase is like, all right, let's go ahead and put down, so a G, and an A.
That looks like an E, sorry. It's like, why is there an E there?
That doesn't make any sense. Why there would be an E there? Okay, C. So then we have, wait, an A, and I'm going to put one wrong, okay? So let's say, all right, so G, so wait, G doesn't live in a pyramid, TC lives in a pyramid, which means G is a,
Purine?
a purine. Okay, so, which means it corresponds to a pyrimidine, right?
Mm-hmm.
Which could be T or C. So I'm going to go ahead and put T in there. What do you think about that?
I don't agree with it.
Yeah. Down DNA polymerase. Retard. So then you go over here, and you have G, A, T, G. Okay, so it made a mistake, right? So DNA polymerase is kind of like a little Pac-Man guy that does proofreading, and it's like, alright. DNA polymerase. DNA polymerase. DNA polymerase is going to be like, okay, 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 and then it's going to chuck out the T. This is wrong. T gets chucked out. Whoa! Oh, chuck out T. And it's going to put the appropriate one in its place. See? So DNA polymerase proofreads it, and it's actually like pretty. It's like its accuracy is like really good.
Okay.
It's like 1 in a million. Like there's an error. I don't know, but hold on a second. It also repairs, so if there's any damage to DNA, it'll come along and fix it.
Mm.
Let me see here. I think that's it. I think that's everything you need to know for DNA
Replication.
Yeah.
Cool, so do you want to stop there for today?
Yeah, let's stop here, and then tomorrow, or whenever we're meeting next, we can talk about
Central
transcription
dogma.
and translation.
Okay.
What do we have down? Is it next weekend? Hope not.
Friday?
So we're meeting in a week? It'd be way better if we met, like, before that. And then we
Let
can
me know.
review.
Just text me your times.
Alright, so, yeah. I'll text you.
Okay.
Okay, bye.
Alright, thanks, Steve.
Uh-huh,
Bye.
bye. I'll upload everything right now. Hey, where do you want...
Can you put it in the drive?
You want it in Google Drive?
Yeah, will that work?
And the video too? Yeah.
Okay.
Do you want the video in there too?
Yeah.
Okay, bye.
Alright, bye.